Hi, Avery. We hope you feel better. And I'm just going to go back and watch this. It's not on there or anything. Okay, related rates. The key to related rates is going to be very similar to what we did with optimization in that we're going to have to write one variable in terms of another is generally what we're doing. So let's see. One variable, or in this case, one rate. And whenever I think rate, I'm thinking derivative, right? So a DRDT, a DADT, anything like that, a rate or derivative. In terms of, and remember, in terms of means using only one other or value or variable. So in terms of one or more other rates. So we'll practice with that a little bit first before we get into the actual related rates. But that's why it's called related rates. We're relating one rate to another, writing one in terms of the other, and then solving for what we need to solve for. Let's look at number 1 in your homework. The radius r and area of a circle are related by the equation area equals pi r squared. Okay, and of course there would be something for you to pull. I don't know, they'd probably give you that. Write an equation that relates the ADT to the RDT. So in other words, the derivative of area with respect to time as it relates to the, and this one should be a fairly easy one for you. Any ideas? We want to relate this to this. Well, what does the ADT equal? But with respect to t this time. It'd be 2 pi r. Now chain it, right? Because it's not with respect to r, it's with respect to t. Y'all remember this when we did implicit differentiation? If you take it with respect, normally we take with respect to x, right? So if we have something like y equals 2x cubed, well then dy dx, I took the derivative of y with respect to x equals 6x squared. Well then I really don't need a dx dx, right? Because that's just 1. But that's really what I did. So if I take it with respect to any other variable, I have to chain it with this part of it. Does that make sense? I can tell looking at y'all's face that doesn't make sense. Okay, let me think. Let's go back a minute. Let's do. Okay, so they asked me to relate, find the derivative of area with respect to t. In other words, how is the area of the circle increasing or decreasing as a function of time? So over time, so the area is increasing 2 square inches every second or something. So that's dAdt they're asking. How would that relate to dRdt? Well, if I take the derivative of this with respect to t, that means every variable has to be followed with d whatever dt. Let me go backwards then. Let me go backwards. Let's say if I asked you to find dy dx here, what would you do? This goes back to that implicit differentiation. Tell me what you do. What's the derivative of the first? Derivative of the first times the second plus the first. What's the derivative of y? dy dx. Here, technically, I could have said that the derivative here was 2 dx dx, but that's just 1, right? You've been doing it, you just don't realize you've been doing it because it's 1, so you don't really include it. Move on. What's the derivative of y squared? 2y dy dx. Why are you following with dy dx? You're taking it with respect to another variable, right? Same thing over here. I'm taking the derivative of a, but it's not with respect to r, it's with respect to t. Does that make sense? If I was doing derivative with respect to r, well, then this would just be 2 pi r. There would be no d, because then dr is just 1, right? Does that make a little more sense? Now that it relates back to the implicit differentiation. I'm going to finish it because I don't want to leave it. Does that make more sense? So whatever variable you're taking it with respect to, you need to follow it with that d whatever. Let's do another. Let's do, that was all because they just said, give me an equation that relates the two rates, that relates dA dt to dr dt. dA dt equals 2 pi r dr dt. How about this one? No, this is another example because they don't have a whole lot of the easy examples like this one. Find an equation that relates dv dt, or actually just find dv dt. Let me say that. Find dv dt. Find the derivative of the volume with respect to time. Did y'all get it? Find dv dr. Find the derivative of the volume with respect to the radius. I could do this, but really that's the same thing as just 4 pi r squared. Do you see? Do y'all see what we're doing? Does that make sense? No? Okay, do dv dx. This just says take the derivative of volume with respect to x. I don't even have to have that variable in the equation anywhere. I can still take it with respect to x. I can say, okay, well, dv dx is going to equal, because that's the derivative of v, right? The derivative of v would be 1 times dv dx equals, now I'm going to do the same power rule. So 4 pi r squared, but I need to follow it. I need to chain this, right? Because I don't know what r is. So now I need to take the derivative of r with respect to x. Just like when I was doing my implicit differentiation with the x's and the y's, because this y, it wasn't with respect to y, I had to follow it with the dy dx. Same thing. How about this one? Find dv dt. And I keep using the dv dt because that's pretty much what we're going to be using. We're looking at the rate over time is what we're doing, how it increases or decreases over time. You get it? Okay. Actually, maybe not. Okay. We're going with respect to t, right? So every variable, we're going to take the derivative with respect to t. So here we go. I'm going to do, and I'm actually probably just going to put this pi over 3 on the outside so I can forget about it a second. If you didn't, that's okay. That's just that coefficient rule that I'm going to use that I'm going to put out there since it's a constant coefficient. Okay. I'm going to do the derivative of the first. So what's the derivative of r squared with respect to t? 2r dr dt. That's the derivative of the first times the second plus the first. What's the derivative of h with respect to t? dh dt. That's all I ask you to do. You don't have to do anything else with it. I just asked you to find dv dt. Sure. It should just be if you distribute it through, but let's see. So you'd have derivative of the first, which would be 2 pi over 3 r dr dt times the second plus the first, which is pi over 3 r squared times the derivative of the second, which is dh. So what you got? Good. This is number 4. I don't want to do too many of them because I don't have a lot for you though. The power of an electrical current is related to the circuit's resistance, R, in ohms, and current, which is I, which is in amps, not amperes, but I think that's just amps, by the equation P, P is watts, that's your power, R, I squared. How is dP dt related to dr dt and di dt? Notice I'm taking with respect to the same variable for all of these. So why don't I just find dP dt? Which is essentially what they're asking you to do. So try it, see what you get. What's dP dt? Y'all got it? Yes. Derivative of the first times the second plus the first times derivative of the second, 2I di dt. And you can stop right there. You don't have to go any further. Yes. Just dipping the edge of our toes into the pool of related rates right now. Part B. How is dr dt? So now they're asking, how is dr dt related to di dt if p is a constant? What changes now? What does that mean if p is a constant? The derivative is 0. It doesn't matter what variable I'm taking it with respect to. The derivative is 0. It's a constant, right? So that means 0 equals what? And then we do the same thing. That's exactly right. That means that all of this, let's see. Now is dr dt and di dt, is it solved? Well, it's not solved for one of the two, but you could easily solve it for one of the two, right? I could say, well, dr dt times I squared equals negative r, and then I could divide by I squared if I needed to, which is more along the lines of what we'll have to be doing. We'll have to be doing some implicit differentiation like this, and then solving for one of the rates, and then plugging in what we know. It's finding those equations that work. Your pictures are going to be key on this, but we won't get to most of that until tomorrow. Yeah, well, then you could finish solving it for dr. So negative r times 2I di dt. I'm wondering if we should jump into one. We haven't really done one yet. That was 7. Let's do one. Let's do an easy one. Number 10. Suppose that the edge lengths x, y, and z of a closed rectangular box. I can do this. We used to do this all the time whenever we were in like. Yeah, that's not half bad. Okay, we have x, y, and z for my dimensions. So x, I don't know where they are, it doesn't tell me. X, y, let the height be z. Suppose that the edge lengths x, y, and z of a closed rectangular box are changing at the following rates, and they give me these rates. They say that the side length x is changing at 1 meter per second. Remember, that's all a derivative is a rate. It's an instantaneous rate of change. So that means as time goes on, that is increasing, so I'm getting longer, 1 meter per second. And then it says that dy dt is negative 2 meters per second. So as I get longer, I'm also getting less wide, right? I'm shrinking in that way. So now let's look at the height. dz dt is increasing at 1 meter per second. So if you got a feel for what this looks like, what's happening here, I'm getting taller and I'm getting longer, but the width of my box is smushing in. Okay. Find the rate at which the box's volume, surface area, and diagonal length, and then they give you an equation for the diagonal length, are changing in the instant when x equals 4, y equals 3, and z equals 2. So this is the same for all. So let's look at part A first. Part A says the volume. Find the rate at which the box's volume is changing at this particular instance. So I need an equation that's going to, just like we were doing before with optimization, I need an equation that's going to relate all this together, right? So let's do that first. How do you find the volume of a box? That's right. X times Y times Z. Now I need to do some type of derivative where I can relate all of these together. So why don't I just do, because this is telling me, right, I do the need and have all the time with these, it helps me. I need, if it says the rate at which the box's volume is changing, that means I need what? dv dt. The volume's changing as a function of time. I need dv dt. What do I have? I have every other variable's change with respect to time. So how can I find dv dt? Well, I'm just going to find the derivative of this. I'm going to say, well, dv dt is equal to. This one's going to be tough. So I got a double product rule here. The way I go about these is I will usually do something like this so I can see it a little bit better as the product of a product instead of trying to go through and figure out what goes with what. So let's see. Derivative of xy. Let's do that first. Derivative of the first was the derivative of x with respect to t, dx dt. So dx dt. Derivative of the first times the second plus the first times derivative of the second. But all that's really just derivative of the first, right? You see that? So I need to times it by z. So that's derivative of the first times the second plus the first times derivative of the second. What's the derivative of the second there? dz dt. Getting into some complicated derivatives here, right? Nothing y'all can't do that. Well, that's not the answer because they want a specific rate of change. But look at what you have. Look at what they gave you. You plug in all those values. Well, dx dt is 1. Y, and they told me all of these too. They said at the instant when x is 4, y is 3, and z is 2. So y is 3, x is 4, dy dt is negative 2, and z is 2. X is 4, y is 3, and dz dt is 1. Three minus 8 is negative 5 times 2 plus 12. I got negative 2. Is that what y'all got? Positive 2. Just kidding. Watch your units. What are your units here? Close. Cubic meters per second. That's exactly right. Meters cubed per second. Because remember, I'm doing the volume changing. So volume changes in cubic meters per second. Does that make sense? Now we're getting into related rates. We're using one rate, relating it to other rates so that we can find the new rate. You try surface area then. Part B says, how is the surface area changing? How do you find surface area? Y'all might need to know that. How do you find surface area of a rectangle or a box like that? Y'all remember? All right, so surface area is the area of each side all added together, right? So we've got x times y, that's the bottom and the top, right? So we got two of those, plus, then we've got the sides here, which are xz, two of those. And then we got these sides, yz, two of them. How many faces does a cube have, or a rectangular box have? 2, 4, 6, and that's all the sides. So it's the area of each face added together. So you tell me, how is the surface area changing? What's the rate of surface area changing with respect to time? Yep. Do the exact same thing this time, and I put SA, maybe just do A, but D, now you're trying to find dA dt, right? At what rate is the area changing with respect to time? These are fun whenever you get them, but you get it's. Yep, and plug in what you know. Anybody do that before you started? You don't have to. I just lots of product rules here. dy times e plus y. And now we just plug in. We plug in what we know. What do we know? We know dx dt is 1. We know dy dt is -2. dz dt is 1. X is 4. Y is 3. And z is 2. I get 2 times, let's see, 3 minus 8 plus 2 plus 4 minus 4 plus 3. -5 plus 2 would be -3. That'd be +1. Did y'all get 0? Where are the answers? Oh, it is 0. Well, isn't that something? 0 what? Meters squared per second. Tell me what that means. Because I'm definitely changing. Things are definitely changing. Surface area is the same. No matter if it increases and decreases at that rate, the surface area is staying the same. That's pretty amazing. The part C on that one, I'll leave that one for your homework for you to do so we don't get bogged down. I think you seem to pretty much get it. But it says the diagonal length, which is the square root of x squared plus y squared plus z squared all under a radical, are changing, and you have to find that ds dt. Does this make sense to you, though, the related rates, how we're relating the rates together to find the rate of one big thing? I'll save the, I don't know. How you feel about it? Tell me how you feel about it. That's not bad. Related rates problems are generally like a sentence or two, and you have to come up with all that stuff. That's when it'll get hard. Like, for instance, let me just do one with you that's a little bit, still not quite as hard as it'll get, but a little bit more. This is called inflating a balloon. A spherical balloon is inflated with helium at the rate of 100 pi cubic feet per minute. So think about you're blowing up a balloon, right? Or the helium's pumping into it. What is this really? The rate of what? The volume. Look at your units and it's a big clue on what you have. So what did they give me to start with? I already know I'm starting with the volume, the changing volume with respect to what? Time. Look at this. Volume, time. Volume, time. That tells me, my units are going to tell me what it is I have as a rate, okay? So they're giving me dVdt. All right, so part A says, and literally that's all they told you though. A spherical balloon is inflated with helium at the rate of 100 pi cubic feet per minute. Then they say, how fast is the balloon's radius increasing? And when you see that increasing or decreasing, that automatically clues you into a rate, right? I'm looking for a rate. How fast is the balloon's radius increasing at the instant? At the instant, so now there's another keyword, right? Instantaneous. At the instant that the radius is, I lost my place, getting so excited, 5 feet. So I said I have dv dt. What do I need to find? What are they asking me to find? dr dt. I need some equation that's going to relate these two things together. And if they don't relate dv dt and dr dt, if I can relate v and t some way, v and r some way, then I can take the derivative with respect to time and relate them both, right? The volume of a sphere. How do you find the volume of a sphere? They will give you that. In this question, they don't. But on your test and on the FRQs and all that, they'll say, given that the volume of a sphere is blah, and I don't know what it is. What is it? 4/3. I don't know. I always think it's 4/3 pi r cubed. Is it? Okay, I think everything is. Every time I need a volume, I'm like 4/3 pi r cubed. Okay, well, I'm glad that's what it was this time. Will that relate dv dt and dr dt for me? Sure, if I take the derivative, right? So now I found the equation. The hardest part, and sometimes you have to draw, most of the time you're going to have to draw a picture for these. This one didn't really need a picture, but we'll get into some pretty grueling ones. But let's do the derivative now. So dv dt equals 4 pi r squared dr dt. Now plug in what you know. Now it's a lot easier because I have everything I need, right? I know that I wanted at the instant that r is 5. I know that dv dt is what? 100 pi. I think it's 100. Yeah, it's 100. It just looks, yeah, it's 100. So 100 pi equals 4 pi times 5 squared dr dt. Can I solve that? Now I'm down to one variable. Of course I can solve that. That's easy. 25 times 4 is 100, right? So if I divide that on both sides, 1 is dr dt. What are my units? There you go. What is it? Yep. Feet per second. Is that minute? Yep. I lost my point. Feet per minute. What does that mean? As helium's put into the balloon, every minute the volume increases by 100 pi, but also every minute, or at the instant that the radius is 5, it is increasing at 1 foot per minute. It's not a constant increase, but yeah. Because I'm thinking about radius, what unit do I do the radius in? Yeah, because see, they gave it to me in the beginning. Yeah. Part B is the same kind of thing. It says how fast is the surface area increasing, and you're going to do that the same way. Okay, I'll leave that one for you to do so you can try. You probably do need to know the surface area of a sphere. I don't know that. I won't pretend I do. Does anybody know? I bet Google knows. Four pi r squared. What do you think about related rates so far? Piece of cake? Oh, I don't even want to think about cake or pie or between turkey metaphors and Thanksgiving. Oh, there you go. 1 through 11. We've done a lot of them.